Stirling cycle is very similar to the Carnot cycle. Let's draw it to start with. So the Carnot cycle in the PV plane, we know what that looks like. Let's draw this cycle, the Stirling cycle. It's very similar. So we're going to have two isotherms, a low temperature and a high temperature isotherm. But now those isotherms are going to be connected by isocores instead of by adiabats. So this is a high temperature isotherm. This is a low temperature isotherm. This isocore has a constant volume. We'll call it VL for low. And this one has a constant volume, high volume, VH. And this kind of cycle is very familiar in terms of a reciprocating cylinder engine. So I would take a look at that on Wikipedia, but we know before we even start that the area inside is the work of the cycle. And we also pretty much can assume, or we can prove, but we also know that there's going to be heat transfer in from 1 to 2 along this hot isotherm, just as there's going to be heat transfer out from 3 to 4 on the lower isotherm. The difference will be that instead of having our double hashed insulation lines on these side connecting processes like we would for the adiabats of a Carnot cycle, now we're going to have isocores that go straight up and down, and they will have the capacity for heat transfer. And so we're going to have to figure that out. And the way we'll do that is we will do that using the first law of thermodynamics, really, and the equations of state. So let's go ahead and also specify in this problem that we really are looking at a calorically perfect ideal gas again, which we might have assumed since we know that these isotherms here look an awful lot like hyperbolas, like we know they would for an ideal gas. We're going to consider if this is helium with a mass of 0.12 kilograms. And this problem is basically being taken out of Sengel's book. We have a high temperature given to us of 3,000 Kelvin and a low, of 2,000 Kelvin and a low temperature of 300 Kelvin. And then we're also told the pressure at the height of the cycle. So the highest pressure the cycle is going to see is going to be 3 megapascals, so 3,000 kPa. And the lowest pressure it's going to see at our state 3 here is going to be 150 kPa. So this is the problem statement. Let's go ahead and write down some governing equations, or better yet, let's write down what we want to find in this problem. Let's say that we want to find the works, specific work, and the specific heat transfer between all of our various processes. And then we might consider also the work of the cycle and regeneration. We'll probably consider regeneration in class. So the governing equations that we have in this problem, we obviously have the first law for cycles. So the cyclic amount of heat equals the cyclic amount of work. In this case, that's helpful because we know the area inside here is not just the amount of work done, but it's also the heat transfer. We have that U beta minus U alpha equals Q alpha to beta minus W alpha to beta. So this is the first law for processes. We also have some important equations of state, right? So the EOS in this case is for helium. That is a gas. So we're going to use the ideal gas law, PV equals RT. And we'll also go ahead and use the calorically perfect law, which we know just looks like du equals CV dt, but we know that CV is a constant when we have a calorically perfect substance. Okay, so that's our basic situation. Let's take a look at each one of these types of processes. So from 1 to 2 and from 3 to 4, we have, once again, isotherms. So what is that going to look like? Well, the first thing we probably want to realize is that du equals Cv dt, dt being 0 on an isotherm, so du is 0 on an isotherm. Okay, we don't have any change in energy on an isotherm. So that means that U beta minus U alpha obviously is 0. So that means that we just end up with that the heat transfer is equal to the work done. And what is the work done in an isotherm? We know from our previous class that's just going to be the integral of PdV from alpha to beta. Well, P in this case is given by RT on V, T being constant. We integrate this and we get RT ln of V beta on V alpha, just like we might expect. So this is exactly like we would expect with the Carnot cycle, no difference here. What we can see then is that if the volume goes up, we should expect heat transfer and work to be positive. If volume goes down, then the logarithm will be negative. The ratio, of the volumes will be negative because it will be less than 1, and we should experience a heat transfer and a work that are negative, and as we've drawn already. So that's for the first part here. What about for our two isocores? So here we have 2 to 3 and 4 to 1. They're both isocores. So we probably want to write down immediately here that the work done on an isocore, the work alpha to beta, we know that's just the integral PdV from alpha to beta. dV is 0 on an isocore, so the work done is 0 on an isocore. What does that mean? Well, we have U beta minus U alpha equals Q alpha to beta minus W alpha to beta, so that is 0. The heat transfer is equal to the energy change. So Q alpha to beta equals, and the energy change is just going to be the integral of Cv dt. Cv being a constant, it's going to be Cv T beta minus T alpha. So let's take a look at this in terms of our problem right now. If we're going from a high temperature to a low temperature, then T beta here is going to be, say, 300, and T alpha will be 2000, so this will be negative. Negative heat transfer means heat's going out. So we can expect that the heat transfer out occurs between 2 to 3, and we have the exact opposite situation on 4 to 1. Oops, on 4 to 1. We have heat going in, don't we? So heat's going out versus here, heat transfer, the sign is positive. This is going to be heat going in, so this is going to be Q4 to 1. So we have heat transfer on all 4 of our processes, which makes this problem maybe a little bit more challenging than the Carnot cycle, but not much, because in both cases we have something easily going to 0. Here the heat transfer, here the work, and for the Carnot cycle we had dq going to 0. So once we have all of these terms worked out, we can easily compute them all for our given problem. What's really missing is our volumes. We don't know VL and VH. What we do know is that at state 1, we have the pressure and temperature. So T1 is equal to TH is equal to 2000 Kelvin. P1 is equal to 3000 kPa. And so we can find V1 using RT on P, and if we just plug those in, we find that V1, which is going to be equal to V low, is just going to be 1.3846. So we'll round this up to 1.385 meters cubed per kilogram. And similarly, at state 3, we know that the temperature at 3 is equal to T low, which is 300 Kelvin, and the volume here, the pressure here at 3 is 150 kPa. Circle those two guys. We can find the third one easily, so V3 is just going to be VH, and VH is, in this problem, 4.154 meters cubed per kilogram. So after we've found VH and VL, it's a simple matter to plug in for each one of these problems, these small problems, to find the work. So work 1 to 2 is going to be R, this is small work, so specific work, R times TH times ln of VH over VL. And plugging those numbers, we find it's going to be 4.563 times 10 to the third kilojoules per kilogram. Work 3 to 4 is going to be RTL ln of VL over VH, and that is going to be a minus 684.5 kilojoules per kilogram. We can find the heat transfer, so that's just finding these values for work and heat transfer. So of course these heat transfers are also known. These are Q1 to 2 and Q3 to 4. Then we find our heat transfer from 2 to 3 and 4 to 1. Q2 to 3 is just going to be CV times TL minus TH, which in this case was minus 5.297 times 10 to the third kilojoules per kilogram. And Q4 to 1 will be the exact opposite, won't it? So this is going to be minus Q2 to 3, I suppose, is the easiest way to write it down. So now we have all of these numbers. How can we really make sense of this cycle? So if we wanted to find the total work of the cycle, we basically would add up the works. We could do that. And we know that the total amount of work done has to be equal to the total heat transfer, and that works out because these two heat transfers cancel with one another. They're the exact same amount. And that brings us to a very interesting topic called regeneration. Stirling cycles are actually really interesting, and there's been a lot of effort recently put into adapting and modifying and developing real Stirling cycles. And the basic idea that makes Stirling cycles so attractive is the concept of regeneration. So what does regeneration mean? In simple terms, it means this. I'm going to try to take this heat that would be delivered out of the system and store it. And then here, where I have heat that needs to be entering into the system, I'm going to release the heat that I've stored over here. Since these two amounts of heat are the exact same, it seems that I can and ought to be able to do that, right? I can store, instead of releasing this heat, I can store it in what's called a regenerator. And over here, instead of trying to add more heat from a different temperature source, I can release the heat that I was stored at this point in the cycle. So as I go through the cycle, I input energy at a constant temperature, high temperature. Here, instead of letting it go, I store it. Then I let go of heat transfer at a low temperature. And then here, instead of adding it, I release the energy I stored over here. So this is the idea of regeneration, and we'll discuss in class a modern context, the slingshot, where this is actually being put to use to help produce clean water for people in third world countries.